Okay, so we're talking about this thing, and the name of it is it's called Colligative Properties, and it's actually sort of this whole suite of things. And these notes, there's a lot of things in them. We're not going to hit on all of them, but I do want to emphasize a couple of things. Last week, if you've been kind of following along, we talked about a couple of ways that you can measure concentration, and those ways that we talked about last week were molarity. And let's see here. We also use the dilution formula. But the big one that I want to remind you of is that there was a formula for molarity. And I'm going to see if I can put somebody on the spot here. Jack, do you happen to remember what the formula for molarity of a solution was? And if you
No.
don't, okay. That's okay. I'm going to go over to Stella. Do you happen to remember what the formula for molarity is?
M equals N over V.
Yep. And the N is moles of what?
Um,
I'll give you a hint.
moles of solute.
Yep, yep, yep. And the reason I'm reminding you of this is because this formula that I'm getting ready to show you is similar, but it is slightly different. So last week, capital M, molarity, was moles of solute, and you said it was over V. What did the V stand for, Stella?
Liters.
Yeah, it was liters. Specifically, it was the volume
Yeah.
of solution. Okay. And Carter, I'm not sure how much of that rings a bell or not, but that was stuff that we worked on concentration wise last week. So this week, what we're going to introduce here, and we'll look more at this on Wednesday, but I wanted to at least sort of plant the seed. There is another way that we can measure concentration, all right? And it's called molality, all right? So very similar to molarity, just a slight change of wording there. Molality is little m, and that is the moles of solute, not divided by the volume of solution, but it is specifically divided by the kilograms of solvent. All right, and it's just a different way of measuring how much stuff we're dissolving into a solution. Okay, now two other ideas here that will be important as we look at this the big idea of today's lesson. Did them a long time ago. I think we understand that ionic compounds, those are always our metals combined with our nonmetals. And ionic compounds, when you dissolve them into a polar solvent, they will separate out into ions, and they are called strong electrolytes because the ions that are now free to move when they are in solution, when ionic compounds dissolve in, those they are able to conduct electricity. That's what electrolyte means. Able to conduct electricity. All right. So when you dissolve an ionic compound, say salt and water, right? The water takes the Na and the Cl and it separates them apart. And now instead of having just one NaCl molecule, you have an Na ion and a Cl ion. All right. Now a molecular compound is like sugar. You've got carbons and hydrogens and oxygens, and that is most definitely not ionic. It is covalent bonding between the carbons, hydrogens, and oxygens. So you don't end up with ions. When you dissolve sugar, you end up with molecules. So you don't actually separate the carbons and the hydrogens and the oxygens when you dissolve sugar in. The sugar just kind of finds spaces in between the water molecules. So the key here is that ionic compounds separate into ions when you dissolve them. Molecular compounds do not separate, all right? And because there are not any ions floating around, those are called non-electrolytes. So like sugar water would not conduct electricity. Salt water would conduct electricity. So I'm going to pause for a second. Any questions so far from you guys? All right. So let me get you guys to consider this, and then we'll jump into sort of the big idea that we're going to get to at the page at the bottom here. So if you, and this is the activity that I'm going to get you guys to do tomorrow, you're going to add some sodium chloride, some salt to ice water. And there's a reason that we do that. And so I want you to consider why we might do that. And if any of you have ever had to worry about putting the coolant in the radiator of your car, all right, there's this thing called antifreeze. Antifreeze is actually ethylene glycol. And there's a reason that we put that into the coolant in our radiator. Um, it would be a really bad thing if all the coolant in our car froze on a cold winter day, because it would the ice would expand, it would crack open the radiator, and all kinds of bad things would happen then. So why do we do this? Why do we put salt in the ice water? Why do we put ethylene glycol in the radiator fluid? And the reason is because of these things that are called colligative properties. All right. And colligative is just a fancy word for any property, all right, that's going to depend on the amount of solute in the solution. So amount of solute in the solution is really what that word colligative means, all right? And the couple things that we're going to focus on today are these. I'm going to talk about freezing point depression. I'm going to skip over here to the next page. And we're going to talk about boiling point elevation, all right, which I like to affectionately refer to as FPD and BPE, freezing point depression and boiling point elevation. Now, even though these are in the notes, we're going to kind of skip ahead there. We're not going to worry too much about the vapor pressure. All right, so boiling point elevation. Now, what we're going to do is we're going to kind of skim right over that because, frankly, I think we can do this a little bit faster, and I think it's a little bit better. Okay, so what we're going to do is simply say this, all right? When we add a solute to a solvent, what we're doing there is we're introducing something that is sort of an impurity, right? Something that is messing up the original solvent. If I think about my container that has water molecules in it, I'm just going to draw the water molecules real simply, right? If I'm going to cool that down and turn it into ice, right, these molecules have to get closer together. And if I insert some salt, and if I just represent the salt with some squares, now I have some things that are in the way. And so for those water molecules to actually form solid ice, they usually just have to get down to 0 degrees Celsius and they form ice. Now you've got this thing in the way. So it's a little bit harder for the ice to form. And since it's a little bit harder for the ice to form, we actually have to cool it down even more. And that is the essence of freezing point depression, all right? So when we add a solute to a solvent, right, one, we lower the freezing point because those solute particles, those solute, whether they are molecules or ions, get in the way. And then the second thing that happens, if we kind of switch this around, if we're boiling water, now what we have to do is we have to think about not trying to come together, but these molecules are trying to break apart, right? And they're trying to fly out into the atmosphere. Well, if I put something else into the water, right? Now what I've just done is effectively all of these spaces up here on the surface where these molecules could take off if they have enough energy and jump into the gaseous state. Well, now I have some stuff in the way. So in order for these water molecules to take off and jump up into the gaseous state, it doesn't require just enough energy to get to 100 degrees Celsius. It requires a little bit more. And so what we have is not only do we lower the freezing point when we add a solute to a solvent, right? We raise the boiling point. Okay. Now, that's me talking for a little bit. How are you guys doing? Can you give me just a quick okay check-in to make sure I haven't lost you there? Let me hear from Carter.
Doing good.
Okay. How about Jack and Stella?
Okay.
Okay. Stella, you okay?
Yeah.
Okay. Now, we're not going to get too much further into the weeds here because what I want to do is I'm going to pause the recording. I want to go into my quote